Okay, right now we're going to look at the three equations we're going to use for electromagnetic induction. And really, there's three equations we're going to use. The first one is called Faraday's law. Then we're going to look at the transformer equation, and then the magnetic force on moving charges. Okay? And really quick, it's easy to get lost in all this math, and we don't want to get lost in all these equations. Okay? The big idea is magnetism and electricity go hand in hand, and you can't have one without the other. And the idea that one can generate the other is what makes modern life convenient. And if you want to boil it down, there's really three key words to help tie this all together. You have to have a changing field, a changing magnetic field that will make an electric field. It's opposing to conserve energy. And then the last one is sideways or perpendicular in terms of the right-hand rules, which is why we use right-hand rules. Because it ends up, you actually can't push an electric charge directly with a magnetic field. It always happens at a right angle. So a way to think of it is maybe just like for a computer screen, like right here, when an electron paints the screen, if you think of it that way, you actually can't move it by trying to push it directly with a magnetic field. It'll always be orientated to the side perpendicular for maximum force. Okay? So let's first unpack Faraday's law. Faraday's law looks really complicated, and it's actually not too bad, okay, if you break it down there. Faraday discovered, Michael Faraday, and he quantified it, so we give him credit, that if you change a magnetic field inside a conducting coil, you can generate what he called the electromotive force, an EMF. What he really didn't realize, what he really discovered was that you could make voltage. Okay? You can give voltage to a coil, which is energy per charge, an energy density to move it. And it's proportional to the number of loops, that's what N stands for, times the area of the loop, the strength of the magnetic field, the cosine of the angle perpendicular, okay, to that coil, which in our case, we're not going to worry about weird angles, but in real life you would have to calculate depending on the angle. We're always going to keep it 0 degrees perpendicular, okay, so you maximize the strength, and then the time of change. Okay, so the voltage can be calculated if you know all those quantities, the number of loops in the circuit, the area of the loop in square meters. Magnetic field is measured in Teslas in honor of Nikola Tesla, and then the rate of change of time in seconds. So see how there's a lot of weird math? What's nice is let's actually visualize this, okay? So notice here I have a light bulb with a coil around it and then a magnet, okay? So you tell me, how come I'm not getting any electric current in here? Why not? Because it's not changing, right? So if I change the field by changing the strength of the magnet, that's what I was doing here, or if I actually move the magnet, that changes the field. In other words, you don't get something for nothing, okay? And that's why there's that delta symbol in the Faraday's law equation. That's why it's delta change, okay? The Greek letter delta. And then that negative just means that it's opposing. Okay, so if you think about it, if I move this to the right, the north pole increases to the right. So if I apply my right-hand rule there, okay, since the field is increasing to the right, it would go into the top of the page. So I would have x's going in and then coming out of the bottom dots. Therefore, since these electrons go the opposite direction, okay, these electrons will end up flowing down, because electrons go the opposite direction as a flow of positive charge. So the way you think of it is, if an electron moves, it leaves a positive hole going the other way. Okay? So notice, as we predicted, if I increase the strength going into the coil, the electrons drift downwards. Okay? Now use common sense. Let's say I want to generate more power. So should I use less loops or more loops? Which one works better? Use common sense, guys. More loops, right? And should the loops be really small or really big? Really big. So one way you can think of it is, okay, there's this idea called magnetic flux. It's the amount of field lines that flow through an area. It's like fishing. So if you catch more fish, right, going through your net, you make your net bigger, you make more nets, you'll get more change, you'll capture more of that energy, okay? So in real life, this would be really annoying to have to do this by hand. So instead of hiring a bunch of monkeys to generate power, here's a cool idea. Why don't you take falling water, right? Or you boil steam using coal or oil to spin a turbine. And then instead of a cheesy little magnet, okay, why don't you have a huge magnet the size of a truck engine? Yeah! Okay, and instead of a little tiny coil, make a coil the size of this room. You see that? And then you can generate megawatts of power. Okay? So in a nutshell, that's Faraday's law. So yes, there's weird math to it, but the idea is more what counts. Okay? It has to be changing and opposing is the way to think of it. Okay?